All right, hello and welcome back. So in this video, we're going to be talking about this topic that's called using a solution freezing point to calculate a molar mass. This is a nice little topic. We're talking about colligative properties again, and really this is sort of just like a problem-solving type topic is the way that I would describe this. I think the hardest thing about this topic is basically just getting organized and making sure you're pulling the right data. So let's go ahead and jump into it. You can see that I've already drawn out some of the information. So I'll just talk through my little picture here and then where I'm getting this stuff. Then we'll go ahead and solve this. So the first thing that I did is actually just draw this little cartoon. I really like doing this just to give us some sort of visual aid to see what's going on and help sort of us, understand the different processes that we're talking about. So in this case, we're told that 42.3 grams of a molecular compound X are dissolved in 85 grams of this formamide. So the key thing here is that, excuse me, we're dissolving this 42.3 grams. So you can see that, maybe I've just added it here and now it's going to dissolve into my 85 grams of solvent. And then this would be my solute. It's important that we're told that it's a molecular compound. That means that we're going to be not having to worry about a Van Hoff factor. It's not going to break into multiple pieces. It's not going to dissociate into multiple pieces. It's just going to dissolve, which is important for the freezing point depression equation. And then this is our solvent, right? And so it's somewhat strange that this formamide is what we're using as a solvent. I definitely would agree with that. But in this case, that's what's going on. So in terms of this equation here, the freezing point depression, the reason that I know that I want to be dealing with this equation is because we're told that the freezing point of the solution is measured to be minus 0.4 degrees Celsius. So that's essentially telling me that when we dissolve this X, that's going to depress the freezing point, right? We've got a solvent, we've got a solute. When I dissolve it, it's going to depress the freezing point. We're told what that depressed freezing point is. So that tells me that I need to sort of pay attention to this equation here. Now, if we're going to be using this equation, then we really need to know like the Kf and also the normal freezing point or the normal melting point for this formamide. And that's actually on this ALEKS data table. So you'll notice that it says, if you need any additional information, use only what you find in the ALEKS data resource. And this is because, different resources are going to have slightly different numbers. So this is in this, if you click on this data tab here, or this data button here, you can find this phase change properties for these pure substances. And what we're looking for here is way down at the bottom, this formamide, and we've got our normal melting point or normal freezing point, and we've also got this Kf value. So that's what we're gonna basically be using as we go through solving this problem. So I went ahead and wrote those down. So again, this freezing point, normal freezing point, 2.57. That's from this ALEKS data right here, 2.57. And then our Kf value, again, is from that same data table. So with this information right here, I can already, the first part of this, any sort of problem solving is just organizing your information. And then once we've organized our information, I can see right away, well, I've got a freezing point that is different than my normal freezing point. So I can actually calculate the change in freezing point. That's going to be this 2.57 minus 0.4. That's going to be what this delta TF is. I can tell that it's changed. I already have my KF, right? So I start looking to see like where I can sort of fill in the gaps here. So if I just take that information, I know that my delta TF is 2.97. So 2.57 minus 0.4, that's going to be equal to Kf, 4.25, times the molality, and the molality is the molality of this solution, right? So that's going to be, the moles of X divided by the kilograms of solvent. And we'll talk a little bit more about that. But right away, I can sort of see, I can solve for my molality. And we do this quick calculation, and that ends up being molality is 0.699, and then I'm going to write the moles for the units for that. That's going to be moles of solute divided by kilograms of solvent, right? So we have to remember what the definition of molality is. The definition of molality is moles of solute over kilograms of solvent. And going back to my picture, hopefully this makes it really easy to see. Well, X is my solute, and then my formamide, that is my solvent. So just looking at this, again, I'm not necessarily like looking at the whole big picture all at once. I'm sort of saying, well, what do I know and what am I looking for? The next thing that I'm looking for is to figure out what this moles of solute is, right? Ultimately, we're looking for the molar mass of X, and that molar mass of X, maybe we'll write that over here. Molar mass of X equals question mark. I know that a molar mass is grams per mole, right? That's really what we're looking for. We're looking for the grams of X per mole of X. So if I know a certain number of, a certain mass of X, then really what I'm looking for is how many moles does that mass sort of represent? What's the relationship there essentially? So all I need to do now is convert basically this molality into basically solve for this moles of solute. So if I take 0.699 moles of solute over kilograms of solvent, and I multiply that by my kilograms of solvent, 0.085 kilograms of solvent, my units of kilograms of solvent will cancel out. And then what I'll be left with is the actual moles of solute that is sort of associated or goes with this 42.3 grams of that solute, right? Essentially, we're solving for, when I dissolve this 42.3 grams, how many moles of it is floating around in the solution, and we keep sort of done that through all these calculations here. So when you do that calculation, you end up with 0.0594 moles of solute. And now basically we're ready to solve our problem. We know how many grams of solute we have. We know how many moles are sort of associated with that number of grams. So if I wanted to find my grams over moles equals question mark, that's going to be equal to 42.3 grams divided by 0.0594 moles. That's going to be grams per mole. And when you do this calculation, you end up with 712 grams per mole. So I'm going to, before I sort of finalize this, I'm going to go back through one more time and just sort of say, what was the process here? I think step one is just being organized, right? Sort of saying, what am I, being shown? What are the relevant equations? What's the data that I can, get from my ALEKS data tab? Start looking for, okay, well, with this information, what can I solve for? Always sort of refer back to, well, what's the ultimate goal? So on and so forth. Now, the last step here is to round this to the correct number of sig figs. So it's a little interesting conversation here. So in this problem, if I just look for, what are the number of sig figs that are, available? So I've got 85 grams of formamide here. I've got minus 0.4 degrees Celsius here. And this minus 0.4 degrees only has one sig fig. But when I do the calculation to solve for my delta TF, this number here, because I'm adding and subtracting, what's more important is how many decimal places do I have? So I'm going to actually end up with 2 sig figs. So this number here, this 2.97, actually contains 2 significant figures, and that's where I'm doing all the rest of my calculations for. So my answer should have 2 sig figs. I know that might be a little bit confusing because we're sort of used to looking for, well, this number here only has 1 sig fig, but if we're adding or subtracting, we need to sort of keep that in mind. And the first step of this process is to subtract minus 0.4 from this 2.57. The result is 2.97. And I'm carrying all my digits here, but we just sort of need to be able to look back and say, well, how many sig figs does this have? It actually has 2 sig figs. Same thing with this 85. And that sort of goes through the rest of our calculations. So this number here, we should round to 2 sig figs. And if I were your instructor, I would say that this is fine. 710 grams per mole. If you write it out like that, that to me represents 2 sig figs, but some instructors out there, they still say that would be ambiguous, and they would prefer you just write it in scientific notation. And I agree that this is better, that there's no ambiguity here, but I would personally accept this, but this is our proper answer. So let's put a box around that. All right, so hopefully that process makes sense, and thanks again.